All right, so we're going to close up 14.2 and go on to 14.3. So this is, again, we're continuing with Seaborn here. Now we've colored like basic formatting of your plots and also color maps. Now we're going to do some of the built-in functions. And one of the things that it really is good at is giving you a lot of different functions to look at distributions in data. So box plots and kernel density plots and um, um, rug plots and all kinds of different things, violin plots, all kinds of different ways to look at the distribution in your data. So we are going to execute these first few cells so that we have everything loaded. And by the way, we set a random number seed to the value is, I think, just due to the way it's meant so that if there's a change in the version, the seed will change, but we're all going to get the same looking plots. So what you get should look like what I get. One of the functions, so first of all, we're going to make a randomly distributed normal distribution of size 100, and then we're going to make a distance plot. So this is or a distribution plot, I should say. So a dist plot will plot the distribution of a series or an array, and by default it will draw a histogram and so this is the histogram and then a kernel density estimate, which is this curve here. And so there's a number of things we can do to control that, but so if we just wanted the histogram, we could use the matplotlib function hist, which depending on what you're trying to do, that might be better. But for a lot of purposes, this dist plot might be just great. So if we don't want the kernel density estimate, if we don't want that curve, we can just say KDE equals false. And then here we can add a rug plot. And there is a function for that, but we can also just add that to our histogram and say rug equals true. So now we'll see the histogram and then these little, it's called a rug plot because it looks like a shag rug. And we can see the individual instances of all those values in our array. We can also control the number of bins. So by default we get 10 bins, but if we want, say, 20 bins, we can specify that. If instead of the histogram we want the kernel density estimate, we can say hist equals false, and then we can say, let's say we want the rug plot still there, we can say rug equals true. This is just describing how the kernel density estimate is done. Basically, you're summing over all of these curves. And this gets just a little bit more into the statistics of how this is done. But here we're generating this density plot, and so this is how we would do it if we didn't want to use Seaborn. We can also shade the shade underneath that curve if we want. And we can use this BW parameter to control how tightly the estimate is fit. So if you can imagine there's a sweet spot between smoothing so much that you can't see any patterns in your data and smoothing so little that you just see all the little in bits. So this BW parameter gives you some control over that. And you also get, because of the way that these curves are fit, you're going to get some parts of the curve that overlap where the end of your data are. So if that in your context doesn't make sense, let's say you have like let's say, like I was dealing with a data set where we had salinity, right? You can't have negative salinity. So if you're fitting a curve to your distribution of salinity, your curve might extend into the negative, and that would look weird. So you can cut. You can say cut equals 0, and it will cut. That means cut at the edges of your data set, and it won't draw that curve beyond there. It's just how it's rendered. And I realize that Seaborn is powerful, but it does hide from the user some of the details of the statistics. So if that feels, if you want more control or to know more what's going on, it might not be for you. But for getting a first look at distributions in your data, I find it's really helpful. So here we can fit a parametric distribution and see how well that fits. So you can control how the fit actually is calculated. So if we want to see bivariate distributions, there's a few different ways to do this. So this is where you're not just looking at variance in X, but also in Y. So we're going to just create a data frame. In fact, I'm going to move this up one. So this is a data frame that I'm just showing you the first 5 rows, but it's got 200 rows of X and Y. And so this joint plot is really handy. So what it shows you is the scatter plot of your data. So you can see the data, but then you can also see overlaid on the X and Y axis these two histograms. So, and the other thing is that this is a very common syntax with Seaborn, where in matplotlib, oftentimes you plot, and the first argument is the X data, the second argument is the Y data, and then the third argument is the color, or the color and the line style. With Seaborn, oftentimes you specify a pandas data frame, so data equals df here. So you're using this data frame, and then within that you can say, I want X to be this column, I want Y to be this column, and then you can actually you can supply a third category sometimes to subdivide your data by, as we'll see in a minute. So this is a common syntax with Seaborn. So it's pretty handy. It shows you all this data, and then you get a Pearson's R and a p-value with associated with that regression. So it's a nice tool. Something similar. Again, we're still using this joint plot, and again, we're just doing a two-dimensional distribution. But instead of just using the standard joint plot, we're going to specify which kind we want, and there's a hex bin. So this will now sum up all of the points within a given hexagon and color it accordingly. So that if you have so many points that they're overlapping and you can't see what's going on, so you have here we have 1,000 points. So with 200 points, you can kind of see what's going on. But with 1,000 points, it's so much that it's better to have some sort of heat map. So it uses this hexagon to generate a heat map. You can also do a proper kernel density estimation. So KDE would be the kind of joint plot here. And now, same idea as this, but we're seeing this kernel density estimate here. We can add to that a rug plot. So we're now one of the things we're doing is, in this case, is we are creating a subplot first. So this is a single axis subplot. What this allows us to do is to plot multiple seaborne objects to this axis. So we say, first we create the figure and the axis objects, and then we run the KDE plot on those data. And so here it's using this more matplotlib style syntax where we have x and y, but then we specify ax equals the name of the axis, and so all three of these things get plotted on the same plot. So we have now this KDE plot and this rug plot on the x and rug plot on the y. We can increase the number of levels in our rendering and change the color map to this cube helix, and we can get some really fancy looking contour maps. So this joint plot function actually uses this joint grid object to manage the figure, and if you want, you can we can work with that directly. So using this, so when we create the joint plot, it creates this joint grid object, which we can then add a scatter plot to. We can set the alpha, and we can add labels to it. So we can do some pretty fancy things. The nice thing about this this rendering is you can see both the individual points and the distribution, the kernel density estimate. So you're getting a lot of information in addition to the distribution along the x and the y axis. I think this is the last part of this lesson. So oftentimes you want to see relationships among more than two variables. Let's say you have, in this case, 4 variables. So we're going to load this data set iris, which is a commonly used example data set in R. So we have these flower measurements, so sepal length and width and petal length and width. And so we can use this pair plot function in Seaborn to rapidly generate a distribution of these things. So we can see when we plot a single variable against itself, it generates a histogram. But when that variable is plotted against a different variable, we see the XY distribution. So this is a really handy way to rapidly see the distribution of your various factors. And just like with joint plot was really under the hood, it was using this joint grid object. Pair plot is using this pair grid object, which we can work with directly if we want. So we can create a pair grid object, and we can put dist plots on the diagonal and put KDE plots on the off diagonal. And we get a little warning about these KW args, which I won't cover today, but there's a little bit more information about that, what that means here. Okay. So I will stop the video here.